So what I have on my screen, what I want to touch on first is metabolic biochemistry. That's what I really want to do. And if we're not able to go through other things, at least let's start from here. And the reason why I want to start here is just to show you the connection between all of this. It's important that when you study this, you try to simplify it by just finding patterns in there. So as you go through this, there's going to be like different pathways and different things to go over. But, always come back, and I'll do that as I teach, always come back to this page right here and make the connection between everything, okay? So let's go ahead and get started. The initial stuff here is just some introductions. So I'll skip through it very quickly, and then we can go into the very first pathway, which is glycolysis, and link all of this together, okay? Now, so starting off with ATP production, all right? And if you remember some of the stuff, the whole purpose of ATP is to drive a lot of metabolic actions, right, that we have going on in the body. So in a nutshell, we need ATP to provide us with that energy. And we need to have ways, right, of making that ATP. Okay, I like to simplify it into two and say we have an oxidative pathway, or a pathway that involves the use of oxygen, and we have a pathway that is anaerobic. Okay, so the initial step that doesn't require a significant amount of oxygen is typically what we like to refer to as a substrate level phosphorylation. Okay, that's the initial step, and that's where glycolysis comes in. Okay, whereas you have another form which is called oxidative phosphorylation. Okay, and oxidative phosphorylation means we're going all the way, we're going through the electron transport chain, but it involves the use of oxygen. So those are just two terms in case you see it differently, but that's what this is talking about right here, right? The anaerobic one is your substrate level, and what we really have going on there is glycolysis, okay? But on the flip side, the aerobic one, in the presence of oxygen, can take us all the way to electron transport chain. And in summary, we're going to make more oxygen there. So more ATP. So that's what we're going to see as we go downwards. Okay. All of this is still introduction here. Your different carrier molecules that we're going to be using. All right. So obviously your ATP carries your phosphate, your phosphoryl groups. Your NADH, NADPH, and FADH2 are your electron carriers. Okay. And I want to talk about that, together with your electron acceptors. You're going to see a lot of NAD. We're going to see a lot of NADH. Here is the difference. If this is NAD, right, usually with a plus, and this is NADH, the difference between them is the H. That H represents an electron. Okay. So it's easier to understand it that way, that NADH is an electron carrier because that H is an electron. It's being carried in there. So if this is my electron carrier, then it means that my NAD becomes my electron acceptor. Okay, because it receives the electron from something and then it becomes NADH. All right. One of the key things we're going to see is going to be the balance between NAD and NADH, right? So sometimes you're going to see some questions that talk about, NADH to NAD ratio and what happens in those scenarios. Bottom line is every ratio is a fraction, right? So if I talk about NADH to NAD ratio, it means I'm talking about NADH divided by NAD. And if they ever tell you that that ratio is increased, then what that means is I have a lot of NADH. If that ratio is reduced, then I have a lot of NAD. So what you have to know as we go forward is, what are the reactions, right? What are the metabolic reactions that require NAD? Okay, and what are the ones that require NADH? There's going to be differences there. Okay, like, you know, some of it is up here. I'll come back to that very soon. But just want to give you guys an introduction. Okay, and the rest of this stuff is just, you know, straightforward. Just know each of the carrier molecules and what they carry. Like biotin carries your CO2, your tetrahydrofolates carry your carbon units, and all that. Okay. And then finally, the last thing here from introduction standpoint before we get into the weeds is just hexokinase versus glucokinase. All right, I believe there's a page in the first aid that has the list of all the different types of enzymes and what they do. And if you go to that page, and there's somewhere, yep, right here. So these are things that I'm not going to go through them because of time, but you should read up on these. Kinases, you know, have one job, and that job is to add phosphates. Okay, they add phosphates. Phosphorylases do the same thing. The difference is the source of the phosphate. Kinases add phosphate by using ATP. They get the phosphate from ATP and then they dump that phosphate somewhere. Phosphorylases do the same thing, but they do not get the phosphate from ATP. They find an inorganic source and use that to make to get the phosphate. Okay. So when we talk about something like a hexokinase or a glucokinase, they're all kinases. So they're adding phosphates to glucose, which is, you know, a hexose sugar, right? Because they have 6 carbons. All right. So both of these enzymes have the ability to be the very first step of glycolysis, all right, to change glucose to glucose 6 phosphate. However, we need to know the location. Where are the areas where you have more hexokinase and where are the areas where you have your glucokinase, all right? So for example, your hexokinase, you're going to see in most tissues except your liver and your pancreatic beta cells, because in your liver and your pancreatic beta cells is where you're going to find your glucokinase, okay? So subtle differences there. In terms of affinity and Vmax, this goes into your pharmacokinetics. Your hexokinase has a lower Km, which means greater affinity, okay? And it also has a lower Vmax, and Vmax just represents efficacy, is how high do you go, how well do you get the job done, okay? So glucokinase, which is what you see in your beta cells of your pancreas and your liver, have a greater Vmax, which means they're more efficacious, okay? And also they turn out to be the ones induced by insulin. I'm going to bring all of this together when we start going into insulin and glucose metabolism, and then it will make sense why a bunch of these actions are happening here, okay? So just introduction, but let's get into it. Let's get into it proper. I want to start off with glycolysis here. And with glycolysis, when you look at the name, there's a lysis in the name, all right? And lysis just means that we're breaking down glucose. So glycolysis simply means the breakdown of glucose, okay? And this is bound to happen, right, if you have the glucose, because there's always going to be that balance about, do I want to break down glucose or do I want to make glucose? So in this case, we want to break down glucose. Why? We have one goal, and that's to make ATP. Okay, so what you need to know is that glycolysis at the end of it is going to yield ATP, but there has to be an investment that goes into it, right? You have to invest some ATP to get some ATP out of it. And you need to know what are the steps where I make this investment and where are the steps where I get the results. So overall, you invest 2 ATP into this, and you end up getting 4 out of it. All right. So when you find the difference, you make 2 net ATP. Okay. 2 in, 4 out. So really, you've made the profit of 2. That's the story of glycolysis. Okay. And so once again, if you come back to this page right here, it shows you all the steps involved in glycolysis, right? And the enzymes involved from glucose to glucose 6-phosphate using either a hexokinase or a glucokinase, right? They add a phosphate there. And then from glucose 6-phosphate, we come to a fructose 6-phosphate, okay? And then from a fructose 6-phosphate, you come down to a fructose 1,6-biphosphate. So we've added a second phosphate. So the enzyme you're going to use there is your PFK1, which is your phosphofructokinase 1, which is a rate limiting step. Remember this, that's your rate limiting step of glycolysis. So the bottom line is we go through a bunch of steps. The end result of it is pyruvate, but the pyruvate is not the focus. The focus is that going all the way along, we have actually produced ATP. So what they're summarizing here for you is, in all of the stuff we just looked at, where did we put in the ATP? Where did we get it out? The very first one is in the very first step, right? Where we went from glucose to glucose 6-phosphate, and ATP was required right there. And then the second step, where we have fructose 6-phosphate to fructose 1,6, your rate limiting step, another ATP investment is going to be needed there. All right. And then the areas where you produce ATP is going to be in this step and that step. So someone may be wondering, well, it looks like if ATP goes in here, ATP goes in here, it makes sense why we have two, right? But then when you come down here, there's only two processes. How do we end up with 4 ATP? And that's because by the time we get to that part of things, well, it doesn't really show it here in the picture. There is a split that happens, okay? So by the time we get down to this point, everything splits up into two. So from one glucose, when we start off with glycolysis, the end result is going to be 2 pyruvates. Pyruvates and pyruvates. How do we know that? Because glucose has 6 carbons, pyruvate has 3 carbons each. Okay, so when you want to go from glucose to pyruvate, you have to split it up. So whatever you do on one side is exactly what you're going to do on the other side, and you end up with double. So that's how we get 4 ATP. So remember this. Now, the other things that are important to note here is going to be the regulation of these steps, okay? What are the things that can inhibit it? So for example, starting off here, when glucose goes to glucose 6-phosphate, all right, glucose 6-phosphate is a product of this step. So it has the ability to exert some kind of negative feedback on the enzymes that got you there. So that's why you see your glucose 6-phosphate can inhibit your hexokinase. Okay, your fructose 6-phosphate is an indirect product of this step as well, because after G6P, the next thing is F6P. So F6P has the ability to inhibit glucokinase to say, we have enough of this, don't send more down. It's a negative feedback mechanism, okay? When you come to your rate limiting step, all right, we have more action here. And also don't forget, the rate limiting step also means that in any reaction, that is your slowest step. So when you look at that, you know, the things that could actually block it, you have to remember citrate is one of them, okay? And you'll see why, because citrate is actually one of the products you have further down the road as you start getting towards the citric acid cycle. And obviously ATP is another thing that could inhibit this step, because ATP is a product. And if I already have the product, I don't want too much of the product's negative feedback. So the concept is whatever is some kind of, whatever you have that is some kind of product along the way could inhibit these steps, okay? Now, there are other things that could activate the step, like your fructose 2,6-biphosphate, which we're going to talk about in the next few minutes, all right? And also AMP, which is the opposite of ATP, can stimulate this step, okay? So let's put that into perspective of fed state and fasting state, okay? Like we said, with glycolysis, the goal is we want to break down glucose, get pyruvate, but ideally, the most important aspect of things here is the fact that we have made ATP. That's the whole reason why we're doing this, okay? So the reason why we're doing this is to make ATP. So let's look at two scenarios. On two ends of the spectrum, you could have glycolysis on one end, okay? And you can have gluconeogenesis on the other end. Now, what is gluconeogenesis? Gluconeogenesis is just making glucose, all right? So it's making glucose, and you're going to see the different ways of making glucose. So we'll go through that eventually. But the bottom line is we want to make some glucose. It is the exact opposite of glycolysis. And that's why when you come back to this picture right here, when you look at this, going downwards, coming all the way towards pyruvate, that's glycolysis. It's the breakdown of glucose. The reverse of it, going back upwards, that's gluconeogenesis. Remember that. It has very similar steps to glycolysis. It's just the reverse. Now, there's going to be some glycolysis steps that are irreversible. We'll talk about that. But generally speaking, gluconeogenesis is the reverse of glycolysis. It's saying, let's get back to glucose, whereas glycolysis is saying, let's break down all the glucose that we can find. Okay, so we like to talk about this in terms of your fed state and fasting state. Now, obviously, when you eat a whole bunch of stuff, but we're going to go under the assumption that fed state means that you have put a lot of sugar into your body. You have put a lot of glucose into your system. So when you are fed and you have a lot of glucose, the idea is we want to break down this glucose and obviously get the energy we can out of it. So if there's one thing to remember, is that glycolysis is favored by being fed. Okay. And then what about when you're fasting? When you're fasting, you don't have enough glucose in your body. So that's not the time to break down your glucose, which also explains why you tend to get tired and fatigued during fasting, because you don't have enough glucose to make the energy. So what do? During the fasting state, we favor more of gluconeogenesis, right? Which is the opposite. So let's find some similarities here. When you look at this, let's use fructose 6-phosphate as the baseline, right, to study this. If you use fructose 6-phosphate as your baseline, let's move towards the right. Going from fructose 6-phosphate to fructose 1,6-biphosphate, that is one of your steps of glycolysis, if you remember, right? That's it right there. Seems very familiar. That is your rate-limiting step of glycolysis with the help of the enzyme PFK1. So you can see that going forward, truly, it's glycolysis. And at the end of the day, what we're going to get out of glycolysis is we're going to get pyruvate, right? But very importantly, we're going to get 2 ATP, all right? So keep an eye on the enzymes. PFK1 is the one that sends us there, our rate-limiting enzyme, okay? So what that tells you is that anything that favors PFK1 or activates your PFK1 is going to help you with glycolysis, okay? Now, on the flip side, going the other way, reversing from fructose 1,6-biphosphate to fructose 6-phosphate, we need a phosphatase. A phosphatase is an enzyme that removes phosphates. So we need your fructose biphosphatase 1, right, to remove that phosphate from this fructose and changes from a 1,6 to a 6. All right. So the 1,6 means we have phosphate at 1 and phosphate at 6. But when we're just at 6, it means the phosphate is just at 6, so we've lost 1 phosphate. And your FBPase 1 sends you back that way. So it's safe to assume that your FBPase 1 is driving you towards gluconeogenesis. Now, why are we talking about this section? The reason why this section is important is because now they introduced 2 additional enzymes, right? And really, it's not really 2 enzymes. It's actually 1 enzyme that is bifunctional, right? And the 2 functional sides of that enzyme is going to be your FBPase 2 and your PFK2. Really and truly is 1 enzyme with 2 functions. Depends on if you're fasting or if you've been fed. That's what determines what's going to happen. Okay, so here's what you need to know. In the fed state, right, while glycolysis is taking place and going from F6 to 1,6, right, so pretty much you can say it's going from 6 to 16, right, you're building up phosphate. That means you're breaking down glucose. You could have an enzyme called the PFK2 that could shunt you slightly away from glycolysis, but it brings you back to glycolysis. It is just a loop. So your PFK2 brings you to your F26BP, right? But it ultimately activates your PFK1 again. So we're still going towards glycolysis. Okay. So in a nutshell, any phosphofructokinase is in favor of glycolysis. It may not be a glycolytic enzyme, but it favors glycolysis, right? PFK1, yes, definitely a glycolytic enzyme. PFK2 is not a glycolytic enzyme, but it is just like PFK1, and it would help you, move forward with glycolysis. That's the message there. That's number one. Okay. Number two is going to be the FBPase. The moral of the story is wherever you see an FBPase, doesn't matter if it's FBPase 1 or FBPase 2, it's sending you in the opposite direction. FBPase is sending you back to gluconeogenesis. All right. And that's what happens when you're fasted. Okay. So in terms of the exact mechanism, right? In terms of the exact mechanism there. So one thing that happens is, yes, when we go towards the right, we get more glycolysis, right? But we also have reduced gluconeogenesis. And when you go to the left, it's going to be the reverse of all that. Okay, so that's the regulation by F26BP, very important high yield stuff right there. And we'll connect it with glycogenolysis and glycogen synthesis when we get there. Now, the next thing that comes after this is going to be what's called your pyruvate dehydrogenase complex. And actually before we go there to the pyruvate dehydrogenase complex, let me do something real quick. Let's create the whole picture of what really happens, okay? Let's create the whole picture. So here is a summary of everything. I think let's start off with the summary before we get into the weeds. When I have glucose, right, and I change that to pyruvate, what's that called? That's glycolysis, right? That's glycolysis. And we know from glycolysis, we are going to get some ATP. But guess what? It's just 2 ATP. It's not a lot. Can barely do anything, okay? Except you keep cycling back and forth, but it's not really going to get you there. So one thing we can do is we can keep going. Now, that's only in the presence of oxygen. So from pyruvate, if we have enough oxygen, then we go through another step where pyruvate gets converted to acetyl-CoA. That step is called the oxidation of pyruvate. Okay, when we change pyruvate to acetyl-CoA, it's called the oxidation of pyruvate. Now, the whole beauty of having acetyl-CoA is that acetyl-CoA can bring us to our citric acid cycle, your Krebs cycle, okay? So you go through a whole bunch of substrates, right? But the bottom line is this is your citric acid cycle. And in the process of going through your citric acid cycle, as you're going to see, you're going to release a lot of, well, just 3 of them. You're going to get 3 NADH, all right? And also you're going to get, these are not the exact steps, but just give an idea. You're going to get FADH2 coming out of it, all right? And like we said, NADH and FADH2, both of these are electron carriers. They carry electrons in them, a lot of them, right? And in this era of cryptocurrency, you can look at it that way. These electron carriers, they have coins. The electrons are the coins, right? That they can go down to the bank and exchange for energy. And what is that bank? That bank is going to be your electron transport chain. Okay, and your electron transport chain, this is where we have our complexes, your complex 1, 2, 3, 4, and complex 5. Okay, so at this point, all of the electrons that we have in NADH and FADH2 can now begin to come down and dump the electrons in the electron transport chain. Okay, and when they dump all the electrons, what they do is they generate a proton gradient, which is pretty much just a bunch of hydrogen ions that ultimately would power complex 5. Complex 5 is also called your ATP synthase. Okay, once you exchange all these electrons, right, you generate enough energy to drive complex 5 to make ATP. And here's the beauty of the whole process. The amount of ATP you can get from this is about 32 ATP. So do the math. 32 obviously beats 2. That's why we go through this process, right? Because we can use more and not rely on glycolysis to give us just 2. However, there are some scenarios where we cannot go all the way and we have to rely on glycolysis, okay? But remember, the key thing is, if I was to draw a line right here, right, what I talked about in the very beginning, right, in terms of ATP production, this level up here is my substrate level phosphorylation. That's what it's called, right? My substrate level phosphorylation, which means we're making ATP without oxygen. That's glycolysis. We're making ATP without oxygen. Then down here is what we're going to call the oxidative phosphorylation. Okay, so the key thing here is I need oxygen to go all the way. And as a matter of fact, the complex where you actually exchange all that oxygen is going to be complex 4. So when we get there, you're going to see that there's going to be certain things that block complex 4 that could affect ATP production. But the point is, if you have oxygen, you go all the way, you make all this ATP. Okay, so why are we talking about that? So when we talk about your pyruvate dehydrogenase complex, what is your pyruvate dehydrogenase complex? This is a complex that allows us to carry out the oxidation of pyruvate, right? This step right here, oxidation of pyruvate, requires your pyruvate dehydrogenase complex. Okay. So what are the key things to remember about this complex? All right, is the cofactors, right? It's a complex because there's so much going on. Well, not quite a lot, but there's some good things going on here. All right. But at the end of the day, the end result is we are just changing pyruvates to acetyl-CoA, period. But they also want you to know that's the beginning, that's the end. But what are the other collateral things that are happening, right? The other collateral things that are happening is just like glycolysis, right? We release NADH. Glycolysis makes some NADH. This makes some NADH as well. Okay. Also, it also wants you to know the cofactors that are in here. You have to memorize this, right? And that's your B1, right? Your B2, your B3, your B5, and your lipoic acid. Okay, so they have it all scattered here, but the easy way to remember it in sequence is remember that this takes B1, B2, B3, B5, and lipoic acid are the cofactors. What's one of the questions that comes out of this is to remember that there is another complex that has the exact same cofactors, right? And that is your alpha ketoglutarate dehydrogenase complex. Remember that. Your alpha ketoglutarate dehydrogenase complex is actually an enzyme in your citric acid cycle. But what you must remember is that when you get there in the citric acid cycle, it has the exact same cofactors of B1, B2, B3, B5, and lipoic acid. Okay. So let's start getting technical with it. One of the key things it talks about here is that this process is activated by an increase in NAD to NADH ratio. okay, is activated by an increase in NAD to NADH ratio. What does that mean? An increase in NAD to NADH ratio tells me that at this point, I have more NAD than NADH. Okay. I have more NAD than NADH. That's what triggers this to happen. Now, why is it important? It's important to remember that because there could be some scenarios after glycolysis where you don't really have enough NAD and you end up shunting to something else. So what am I talking about? Let's bring it up here. No, maybe not up here. I know it's somewhere. I'll find it. Yep, there you go. There you go. All right. So if you take a look at this, if you take a look at this right here, that's glucose and that's pyruvate. So do you agree with me that this step is glycolysis? Right? Because what's glycolysis? It's changing glucose to pyruvate. And then now we've seen that after we have pyruvate, pyruvate can now change to acetyl-CoA in the presence of oxygen, right? With the help of my pyruvate dehydrogenase complex, right? And in that process, once again, NAD is being converted to NADH, which is why to actually move forward with this, right, I need to have more NAD and less NADH. And we know, like we've seen, that if you can go down this route and make acetyl-CoA, then maybe you can go all the way to your citric acid cycle, and then from there, your electron transport chain, and you end up making a whole bunch of ATP, okay, if you can go all the way. But the moral of the story here is that pyruvate does not always change to acetyl-CoA. Pyruvate can change to other things, okay? Other things, there could be alanine for specific purposes, right? And we're going to talk about your Cori cycle and your Cahill cycle. Pyruvate can change to oxaloacetate if you're trying to restart gluconeogenesis, right? Or pyruvate can change to lactates, which is my Cori cycle. Very important, okay? Now, here is the deal. Pyruvate changing to lactate is typically triggered by an absence of enough oxygen, okay? And also by my NAD to NADH ratio being different. Because these are the tiny details you have to remember that you're going to show in the questions. Going from pyruvate to acetyl-CoA, all I needed was NAD. But to go from pyruvate to lactate, I need something different. I need NADH. Okay. So based on how much NAD or NADH you have, you can go either way. All right. Remember this, very important. If I have a lot of NAD, I'm coming down to acetyl-CoA. But if what I have is NADH, I am not coming to acetyl-CoA, I am making lactate. This is typically what happens when exercising, right? You end up making lactate. Lactic acid builds up in the muscles. You get all that pain and soreness, okay? And the thing about it is lactate has a way of reversing back, to glucose at the end of the day. That's the Cori cycle. We'll deal with that later, all right? But the whole essence of going to lactate is, but you can write this down if you don't have it in your notes, you're not familiar with this. When you make lactates, right, you are able to just keep recycling glycolysis over and over and over again, all right? Because you cannot go all the way down to electron transport chain and make all the ATP you need. So what you can do is, I know glycolysis makes only 2 ATP, but if I do this several times, then I can make enough ATP. That's the whole process right there, okay? Now, one of the things I want to link this to before we even proceed is your alcohol metabolism, right? How does that tie into this process? Because believe it or not, right, it plays a role, okay? So if you come all the way back up here, right, and I don't know why they have it up here, but if you take a look at this, okay, this right here, when you consume alcohol, right, there are two enzymes involved in the breakdown of alcohol. The first one is going to be your alcohol dehydrogenase, which will change the alcohol or ethanol to acetaldehyde. Then additionally, you need an acetaldehyde dehydrogenase that could change it to acetates. Okay. But watch this. To break down alcohol to acetaldehyde, we yield NADH. Okay. Just like glycolysis and everything else. And when acetaldehyde changes to acetates, I yield NADH as well. Okay. So do you agree with me that consuming a lot of alcohol results in an increase in NADH, which is all, you can also say that as an increase in NADH to NAD ratio, right? So having alcohol in the system, a lot of alcohol results in what? A lot of NADH. Okay. So the thing about it is, if I have a lot of NADH, right, guess what's going to happen? All right. If you come back to these steps right here, if you come back to these, since alcohol requires a lot of NADH, am I going to be, I mean, since it's making a lot of NADH, right, not NAD, am I going to be coming down to acetyl-CoA? No. Instead, what do? I have to go through a reaction that already has, that needs NADH, because that's what I have. And what is that reaction? It means changing pyruvates to lactates. It is for this reason that lactic acidosis is one of the common symptoms you can see from alcoholism. Key points, right? Because alcohol increases NADH, period. Now, they will describe it as increasing NADH to NAD ratio, but what that really means is that it increases your NADH, all right? And when NADH is up, one of the key things you see there, right, is your lactic acidosis, okay? Now, other things that can happen, and if time permits, we'll come back to them, is you can get fasting hypoglycemia because of reduced gluconeogenesis, okay? And why? Why is that going to happen? Because if you come down to these steps right here, you have to know, okay, here are other examples of reactions that require NADH versus NAD, right? So let's run through it again, because these are some of the same things we've seen. Coming down right here, looks familiar. It's glycolysis, glucose to glyceraldehyde, 3-phosphate, your PEP, pyruvate. This is glycolysis at the end of the day. Glycolysis yields NADH, okay? But we've seen that going from pyruvate to lactate, it uses up NADH and actually yields NAD, okay? So what this is showing you here is the reactions, all right? I think what they have here, the solid red lines, okay, the reactions that actually use up NADH. Okay, so one of those reactions is in the glycolysis process, right? Where glycerol is yielded, but glycerol can get converted to triglycerides because glycerol is the head of your fatty, of your triglycerides, right? Your triglycerides is your glycerol and 3 fatty acids. So NADH pushes you towards that. Okay, this is a mechanism behind the fatty liver disease you see in alcoholism. All right, so if you get a question on that, remember it's all about NADH. The alcohol increases NADH, and when you increase NADH, it could actually make you produce a lot of glycerol, as you can see, and all that glycerol will result in fats. Then you get a fatty liver. All right. NADH is required to make lactate as well. So if alcohol increases NADH, lactic acidosis sets in. This is how you put it together. Okay. Your NADH actually promotes ketogenesis, right? NADH promotes ketogenesis and fatty acid production. So that's the reason why you can see ketoacidosis in alcohol patients, because it changes the acetyl-CoA to keto acids. Okay. It can also increase the production of fatty acids from acetyl-CoA. NADH is right there as well. you need NADH, which would actually promote more fatty liver. All right, so that's the concept in this picture is the red arrows tell you the places that use NADH. So therefore, if anything gives you NADH, these reactions would happen. And one thing, if there's anyone you remember, is that alcoholism breeds NADH, right? Because when you're breaking alcohol, you get a lot of NADH, right? And then the final one there is, in the presence of NADH, we can change oxaloacetate to malate, right there. Remember this. Oxaloacetate can change to malate in the presence of NADH. But oxaloacetate at the same time, we know is one of the requirements for gluconeogenesis. But if gluconeogenesis were happening, the oxaloacetate would not be coming to malate. It should be going to PEP, right? So you can see oxaloacetate sitting in the edge right there. It's at a crossroads, and it says, I can go two ways. I can either go to malate or I can go to PEP. But if I go to PEP, I will make glucose, gluconeogenesis. But if I go to malate, that's on the other side of the road. I am not going to make glucose. Okay, guess what? NADH sends you to the other side of the road. This is the reason why alcohol patients can have hypoglycemia as well, right? Because if oxaloacetate is changing to malate, you're not going to make glucose. That's moral of the story here, is what they're trying to show you is these are the places where NADH could alter your reaction and take you in an opposite direction, okay? I hope this is making sense and coming together. It's a lot, but when you just keep studying it, you know, it will all link up, okay? All right. So let's go over to your citric acid cycle, okay? Let's go over to your citric acid cycle. All right, it's a continuation of everything. So once again, if you link it together, we know that once upon a time, we had what? Glucose. Glucose changed to pyruvate, and that process is called glycolysis. Then we said in the presence of oxygen, right, pyruvates could go through your pyruvate dehydrogenase complex that had those substrates, not substrates, those cofactors of your B1, B2, B3, B5, and lipoic acid, and then change to acetyl-CoA. But once we have acetyl-CoA, then we can enter into the citric acid cycle, also called your Krebs cycle, okay? And the whole essence, the importance of your Krebs cycle, remember this, is just to generate NADH. That's the main goal, because NADH, these are electron carriers, and FADH too, as well. These are electron carriers that we can take all the way to the electron transfer chain and exchange them for a lot of ATP, okay? So that's the whole concept. So what are the key things to memorize here? Well, number one, know the substrates, right? Know the substrates of your citric acid cycle. So there is a mnemonic that people use, right? Well, yeah, not this one here. Here it says citrate describes sadness. No, the one that is often used is, can I keep selling, soup for money, officer? All right, let me write it down. So it's, can I keep selling soup for money, officer, right? You can call it sell soup, sell soap, sell anything, all right? So obviously the C is for your citrates, I for isocitrate, K for your alpha ketoglutarate, all right? S for your succinyl-CoA. The second S is for succinate, F is for fumarate, M malate, and O oxaloacetate, all right? Very important. Now, you need to know the steps where NADH is produced, okay? So the first one is after the I, okay? NADH is produced there, all right? And then back to back after the K, all right? NADH is produced there. So let me highlight it here. NADH, NADH, right? And then NADH as well after the M. So I, K, and M, right, give you NADH. I keep money gives you NADH. Remember that. When I keep money, I am making NADH. Okay. FADH, easy way I try to remember this is that FADH comes right before F. So, right. So going from S to F, right, somewhere in there between my S, and my F, right, is where I have FADH, right? Important to remember that as well. Okay. And one other key thing to remember, like we mentioned earlier, is that your alpha ketoglutarate dehydrogenase is right there. That's the one that takes you from a K to S. And it's the same thing. Well, it looks very similar to your pyruvate dehydrogenase complex because this is where we have B1, B2, B3, B5, and lipoic acid, okay? And then finally, even though the whole goal here is to make some NADH because we know we can go to the bank at the end of the day and exchange all this NADH for a lot of money, which is ATP, okay? However, we still make GTP, right? We still make some GTP right here. And that's a very popular question. You might have come across it already, maybe not. If you haven't, it's coming. You must remember the step where GTP is made, okay? And that is between succinyl-CoA and succinate. You must remember that step. So the easy way I try to remember myself is I always say that, obviously, if you want to make money, you got to sell something, right? So when I sell soup, I make money. What's that money? GTP. So that helps you remember that GTP is made between succinyl-CoA and succinate, which is the selling of the soup. When you sell soup, you make money, you make GTP. Remember that, or come up with whatever way helps you remember, but it's important to know which step GTP is made. Okay. Let's see, what else is important here? The other thing also don't forget is oxaloacetate, you can see, right, is one of the players that we have here, okay? And malate is one of the players we have here, okay? And you can see that that is one of the steps that NADH was made, okay? It is one of the steps that NADH was made, right? To go, what's it called? To go from malate to oxaloacetate, okay? However, you can have a reverse reaction as we've seen, right? You can have oxaloacetate going back to malate. Now, that is not citric acid cycle. That is outside of the cycle because the sequence is in the citric acid cycle, malate changes to oxaloacetate. That's the citric acid cycle. But we also see that in the presence of excessive amounts of NADH, which could actually come from alcohol, we can reverse this and actually take oxaloacetate and change it to malate. Okay, now don't forget, we saw this. The problem with that is, if you look at this, glucose, pyruvate, and oxaloacetate and all that, right? In order to make, to go through gluconeogenesis, right, we have a way of actually bringing that pyruvate to oxaloacetate, and then oxaloacetate looping back around, and ultimately we get glucose back. That's your gluconeogenesis, okay? So in a nutshell, let me make this as simple as possible. I don't want to complicate this. If I look at oxaloacetate as a focal point, then what you need to remember in this focal point in the citric acid cycle is that oxaloacetate, right, obviously can continue in the citric acid cycle, right, by changing to citrates, right? So that's one. Oxaloacetate has an option of actually reverting through a series of steps, obviously, but it has the ability to revert back to glucose. That's two, okay? or ultimately it can change to malate. It can reverse itself and change to malate. Okay, those are the three options oxaloacetate has sitting right there. Okay, now the third option, right, means nothing. It's just, yeah, oxaloacetate change to malate. But what to remember is that's triggered by NADH. And then the second option, don't forget, is gluconeogenesis. Okay, and think about it, you can't do all three at the same time. You have to pick and choose what you want to do. So that's a reminder that if for any reason oxaloacetate decides to just keep going back and forth in this cycle, guess what we're not going to make? We are not going to make glucose. And that's where hypoglycemia can actually set in, right? Remember that, connect this together, right? So this is how you can link your citric acid cycle with what happens in a patient who's experienced alcoholism, okay? All right. And then finally, final step of all of this, your electron transfer chain. This is where it all comes together. Everything we've done, the end result is to get here and make as much ATP as we can. Ideally, make 32 ATP out of this. Okay, so all those NADH that we've been accumulating from glycolysis, oxidation of pyruvate, citric acid cycle, and also the FADH2 as well. We bring all of those here and we dump it here in the electron transfer chain. And look at it, the terminology I've been using, what is this called? This is your oxidative phosphorylation because it depends on oxygen. And if you must remember this, the complex where you actually use the oxygen, where it all comes together, is complex 4. Remember that. It's oxidative because we're using the oxygen here, but the exact complex where you're using the oxygen is complex 4. Okay, so with your electron transfer chain, right, like you can see there are different complexes, 1, 2, 3, 4, and 5. And different things can happen at those different places. Okay, so ideally, what you get is the NADH that we've talked about, they come here and they get exchanged, right? Now, this is happening in the mitochondria, by the way, very important. Glycolysis happens in the cytosol, but this is happening in the mitochondria. This is a powerful process, okay? So obviously you can see that this membrane you have here is your inner mitochondrial membrane. That's the mitochondrial matrix, and that's your intermembrane space. So we're in the mitochondria, okay? So what are the tiny details to remember is, how does all the NADH and stuff from the cytosol get in here, right? They get in through what's called the malate aspartate shuttle, right? Or the glycerol 3-phosphate shuttle, remember that, okay? And those are just the vehicles for bringing the NADH down in here, okay? Now, the NADH can go straight to complex 1, okay? They can go straight to complex 1, as you can see here. And when they get to complex 1, they get converted back to NAD. And what does that NAD do? Now NAD is free and available for all the processes that require NAD, such as glycolysis, oxidation of pyruvate, citric acid cycle. These are all NAD requiring processes. So now we get free NAD that can go back and drive all of those, okay? But is the next change. When this NADH changes to NAD, guess what's missing? It's lost the hydrogen, right? Where did the hydrogen go? It fell through right here. That is that hydrogen. So the NADH carried the hydrogen for as long as it could. It brought it to the electron transfer chain and it dumped it right here and walked away as NAD. But we have hydrogen in the intermembrane space left there. Now, FADH2 does something very similar. The only unique thing to remember about FADH2 is that it's 2 for 2. FADH2 comes straight to complex 2. That's all you need to remember about it, okay? But it's doing the same thing. It's trying to dump its electrons in into membrane space, but it starts off with complex 2, okay? And then, so that goes on, and what we're doing is, we're accumulating hydrogens in this intermembrane space, right? And that is what we call, right, the proton gradient, because hydrogens are protons. technically from a chemistry standpoint, but there's also electrons as well. Okay, so that's why it says like the passage of these electrons will result in the formation of what's called a proton gradient. Okay, so all this hydrogen that we have right here, that's our proton gradient forming. But don't forget, once we get to complex 4, this is where oxygen comes in handy. This is how biochemistry ties to your respiratory system. The oxygen you have coming in from the lungs, right, going through the alveoli into the bloodstream, this is where it could come in handy. That oxygen could carry out the reaction in complex 4, right? That will actually contribute to the formation of more proton gradients, right? But it's like a gate step before we get to the final step. And what's the final step? The final step is complex 5. Complex 5, I think we mentioned this earlier, is called your ATP synthase. All right? Because in complex 5, what's going to happen is all the hydrogen that you've been building up, right, will then drive their way up through complex 5, right? So if complex 5 is like a generator, right, the fuel that complex 5 needs is hydrogen. So all the hydrogen we've built up will now power complex 5, and the end result of that is what? ATP. Lots of it. That's the reason why complex 5 is called ATP synthase. You have to remember this. That is an actual exact step in the electron transport chain where the ATP is made. It's not made on complex 1, 2, 3, or 4. It's actually made on complex 5. So you can see every complex has its role. 5 makes ATP, 4 is for the oxygen, 1, 2, 3 is for the NADH and FADH2 to dump the electrons and create that proton gradient, and that's it. Okay. So ultimately, at the end of the day, right, remember that 1 NADH gives you about 3 ATP, all right, and 1 FADH2 gives you about 2 ATP. So when you add it together, that's how you end up with 30 plus ATP, and the job is done. Okay, so from the standpoint of things going wrong, what we like to look at in electron transport chain is, okay, now we get it. Now we get the whole process. We get why we had to go through glycolysis and your citric acid cycle and all that. But things can go bad here. And what are the different ways that things can go bad here? First one could be the use of electron transport inhibitors. Okay. Now, in all of these, there are different things going on. The actual electron transport is really through complex 1, 2, and 3. Yeah, a little bit of 4. But mainly complex 1, 2, and 3 is where we have the electron transport, because that's where we have the NADH and the FAD action dropping those hydrogens. Okay, so if we say that something is blocking the electron transport, then it means that it is preventing us from putting hydrogen in here. And that's described as causing a reduced proton gradient. Okay, so if I block my proton gradient, remember the proton gradient is that fuel, is the gas we need to power this vehicle. So if I don't get this proton gradient, then I cannot power complex 5, right? And that's exactly what you see right there. So what are examples of this? Rotenone is a very good example, but remember rotenone blocks complex 1. But remember complex 1 is all about dumping electrons, so it fits into the category of electron transport inhibitors, right? Your antimycin A, right, is a complex 3 inhibitor. All right, it's a complex 3 inhibitor. So once again, it blocks the transport. Cyanide, right? We'll see this in hematology. Cyanide, carbon monoxide, right? Your azides, these are complex 4 blockers. All right. So they also, because complex 4, yes, is known for oxygen, but there is still some electron transport going on there. Right. So when these things block complex 4, then we cannot get that electron transport, and ultimately we cannot power complex 5 at the end of the day. Okay. So that's what you call electron transport inhibitors. They're mainly 1, 2, 3, but you can also have 4 as well. Okay. So in a nutshell, we can say this is 1, 2, 3, and 4. Okay. Now, the other group you can have is what's called your ATP synthase inhibitors. What is your ATP synthase? Complex 5. So this is your complex 5 inhibitor. All right. So it doesn't stop you. Here is the deal. it doesn't stop you from carrying out electron transport. Electron transport will proceed, but the bottom line is at the end of the day of that electron transport is going nowhere fast because this is gone. Okay, so electron transport proceeds. We still have a proton gradient, but we just cannot make ATP. Okay, we just cannot make ATP. Classic example of complex 5 inhibitor is going to be your oligomycin. You have to remember this. Oligomycin will put you right there. Okay. And then you have your uncoupling agents. All right. You have your uncoupling agents. So with your uncoupling agents, okay, what they do is, let's start off with, let's start off with the word coupling. Because once you understand coupling, then you understand uncoupling, right? Because the electron transport chain is considered to be a coupling reaction. A coupling reaction is when, you know, one reaction combines with another one to get an end result. So what's being coupled here? Who are the members of this couple, right? One is the electron transport, all right? And if you look at the notes, it has it right there. The electron transport that gives you a proton gradient is now coupled to oxidative phosphorylation. So you have electron transport, then you have the oxidative phosphorylation, which is where you have the oxygen, right? And the ATP, all right? You put them together, that is a coupling, right? So an uncoupling agent will separate the two. It kind of puts a demarcation right here. It says electron transport may proceed, but it would not be able to power your final steps. Okay, so how do you uncouple? What uncoupling agents do is they increase the permeability, right? They increase the permeability of the membrane, okay? And it makes the membrane leaky. And when the membrane is leaky, then what's gonna be happening is that all the protein you're building in here starts leaking outwards. It starts going back towards the mitochondrial matrix, okay? And if that proton leaks, then we don't have enough proton gradients to actually power the last step, okay? So that's why ATP synthesis is going to stop. But guess what? Do we still have electron transport? Yes, we still have electron transport, but the electron transport is a waste because we are leaking. It's almost like your car has a leaking gas tank. So you can keep putting gas in, but it's going to keep leaking and you're going to have to keep refilling. So all they're doing here, you must remember this, very importantly, uncoupling agents generate heat because the system is working harder than normal because we have a leak, pretty much, all right? We have a leak, we're losing these protons and we're not able to generate ATP, okay? So what are examples of your uncoupling agents, right? Your 2,4-DNP, right? Your dinitrophenol, all right, can do this, right? Aspirin, especially after overdose, can do this as well. A very common one is thermogenin that you see in brown fat, right? Brown fat is brown because it has more mitochondria than white fat. Thermogenin is an uncoupling agent. That's what, like the name implies, thermo, right? It generates heat by ensuring that all your electron transport does not generate enough protons to power your ATP production, okay? So that's it. That's a summary of your phosphorylation from your substrate level phosphorylation all the way down to your oxidative phosphorylation, and that's your process of making ATP, okay? Once again, the very beginning, which is glycolysis, predominates in a fed state, okay? Now, on the flip side, let's talk about gluconeogenesis, okay? And like we said, gluconeogenesis is just the reverse of glycolysis. Gluconeogenesis simply means we are making glucose. We're making new glucose. That's what the neo in the name stands for, new glucose, okay? Why? Because there's actually a way of making old glucose, okay? There are two ways you can get glucose if you need them. You can get glucose from gluconeogenesis, or you can get glucose from glycogenolysis, okay? Because what is glycogen? Glycogen is just a storage form of glucose. So if I can break down my glycogen, I can get back all the glucose I have saved up, right? So that's the thing. If you need money, there are two things you can do. You can either find a way to make new money, or if you have a savings account, go to the bank and get your money from the bank. That's what this is. Gluconeogenesis says we need money, which in this case is glucose, not dollars. We need money. We're going to go out, get some work done, make some new money. That's gluconeogenesis. Glycogenolysis says we need money, we need glucose, but we're not necessarily going to make new glucose. We're not going to make new money. We have some money saved up somewhere. Let's go withdraw some of it. That's glycogenolysis. That's the difference between them, right? One of them is a withdrawal activity. The other one is new money coming in, right? Of which if you make extra, you can put it back in the bank and save it, right? And so you can withdraw it when you need it. So I think that's what we're going to be doing next, just talking about some of the differences here. Okay, so coming back to this page once again, right? When you look at this, like we said, coming down is glycolysis, but the reverse is gluconeogenesis. However, here is the beginning, and I think the most important step. When you look at it, going from PEP to pyruvate was a glycolysis step. All right, the enzyme that did that is pyruvate kinase. Pyruvate kinase changes you from PEP to pyruvate, and that's the end of glycolysis. You would notice that a bunch of these have, arrows going backwards, okay? But in this step, it's just a single arrow. There's nothing going backwards because you must remember this. Pyruvate cannot just turn around and change back to PEP. It cannot, okay? So the only way we can reverse this to actually go back to gluconeogenesis is to let that pyruvate change to oxaloacetate, not acetyl-CoA, not lactate, but oxaloacetate, and then oxaloacetate can shunt back to PEP. So that is how, so we don't just turn around, we make some kind of U-turn, right, to kick off gluconeogenesis, key point, right? Pyruvate has to go to oxaloacetate, right? And oxaloacetate can now take you back to PEP, right? And the enzyme to use there is your pyruvate carboxylase, is the one that changes you to oxaloacetate, right? And then your PEP carboxykinase will bring you back to PEP, all right? So two important steps. So let's bring it back to perspective here. These are the two enzymes we just talked about. Pyruvate carboxylase and PEP carboxykinase. Right? What did they do? From the very beginning, pyruvate carboxylase help you change to oxaloacetate. Okay, it will help you change to oxaloacetate so we can start the process of the U-turn. But remember that it's a carboxylase, so it's going to require biotin. Okay, it's going to require biotin. Now, it's also going to require ATP, and it could be activated by acetyl-CoA, but remember the biotin part is important because it's a carboxylase, okay? And then the next step, right, is going to be your PEP carboxykinase, which will change oxaloacetate to PEP, okay? It will change oxaloacetate to PEP, and once oxaloacetate changes to PEP, now we're on the way, okay? We're on the way. Now, the other things that you would also see is your phosphatase enzymes. These are important, your phosphatase enzymes. Okay. So for example, the first one is your fructose 1,6-biphosphatase 1. This is the same enzyme, right, as your FBPase 1. I want you to connect the dots. This is your FBPase 1, all right? And just for memory's sake, all right, let's bring you back to where you saw it. That is it right there, your FBPase 1, okay? What is it doing? It's taking you from fructose 1,6-biphosphate back to fructose 6-phosphate because we know if we're going towards the left, we are going towards gluconeogenesis. Okay. So remember that. And this is something I like to do. And, this is when I was studying, this is how I studied. And, I always recommend this. When you study things like this, especially biochemistry, and not just here, a lot of them, connect the dots, right? Don't read each section in isolation. Don't just read each page of the book like, okay, I've read today, I've done some studying today. Connect the dots, and that's why you're going to see me going back and forth. Because when you connect the dots like that, it just makes it easier, and it helps you bring this, bulky information into a very, very small concept or summary. Okay, so that's just by the side. All right, so just wanted to show you guys once again your FB page right there. Okay, and then finally, this is a very important one. Your glucose 6 phosphatase, like the name implies, it's a phosphatase, so it is removing phosphate. All right, it is the reverse of your glucokinase and hexokinase. Right, remember that this is the reverse of glucokinase or hexokinase, because glucokinase or hexokinase changes from glucose to glucose 6 phosphates. Now this one is taking us back from glucose 6 phosphates back to glucose. Okay, so this is the final step. This is the final step. Once you get past this, now you have glucose. You have completed gluconeogenesis. Okay, so what is the one key thing, right, that you have to remember here, right, is that your glucose 6 phosphatase, right, occurs primarily, right, this reaction you see mainly in the liver. All right. So your muscles don't have this final step. So muscles cannot participate in gluconeogenesis. Key points. All right. These are the buzzwords that you're going to see in questions. Remember, your muscles cannot make new glucose. So what that tells you that if my muscles need glucose, what are they going to do? They're going to go to glycogenolysis because they can't come here. The muscles have to go here. Remember that. The liver can do both, right? The liver, that's why your liver is so crucial. The liver can do both, okay? But not the muscles, all right? Because of this final step, glucose 6 phosphatase, all right? It's not there, all right? Then it also tells us about other ways, right? Other ways that we can actually make glucose, right? Your fatty acids can actually contribute towards making glucose. So it's very unique. Now we're going from fats to glucose, right? And specifically, it's your odd chain fatty acids, okay? So the thing about it is I like to call this the PMS, all right? So PMS means I go from propionyl-CoA, let's go, to methylmalonyl-CoA, to succinyl-CoA. Okay, so that's the PMS. Remember that, PMS. And what's the beauty here is succinyl-CoA sounds familiar, right? It's a citric acid cycle derivative. Okay, it's a citric acid cycle derivative. And I know that if I can get to succinyl-CoA, I can eventually get to oxaloacetate. And if I can get to oxaloacetate, then I can convert back to PEP and I'm on the way up. That is how fatty acids can contribute, right, to gluconeogenesis, right? Let me bring it back here again and show you in the big picture. Okay, this is it right here. Okay, oh, look at that. So your odd chain fatty acids and certain amino acids as well, like your isoleucine, valine, methionine, and threonine, you have to remember these. These are substances that can actually help you. All of this here can help you make new glucose because they can change to propanyl-CoA, right? Propanyl-CoA can become methylmalonyl-CoA and then succinyl-CoA. That is your PMS right there. Okay, and if I can get to succinyl-CoA, Then I will continue along the citric acid cycle. But once I get to oxaloacetate, I loop around this way and I'm on the way up to glucose. Okay, so that's what you have to remember, is that these right here, right, put it in your notes. These help you with gluconeogenesis, right? Because they go through PMS. From PMS to the citric acid cycle, and from a citric acid cycle, guess what? Once I can get to oxaloacetate, I am on my way up. And once I get in here, I will go all the way up to the glucose. Now, once again, remember, this has to be in the liver, because if this was muscle, we will get stuck right here because muscles don't have glucose 6 phosphatase. This is how you connect the dots. Okay. All right. So remember, talking about details, it's your odd chain fatty acids. Your even chain fatty acids, you're not really going to do this because the even chain fatty acids would yield only your acetyl-CoA equivalents. Okay. So that's gluconeogenesis for you. All right. We're going to come to some more stuff as very soon, right? Like glycogen synthesis and glycogen breakdown. Okay. But let's talk about the pentose phosphate pathway, right? Also called your HMP shunt. So look out for both names. Sometimes called the HMP shunt, sometimes called the pentose phosphate pathway, the same thing. What you need to remember about this is that your pentose phosphate pathway comes out of glycolysis. It's all connected. It comes out of glycolysis, right? In the very beginning of glycolysis, we decide to take a short break, go out of the cycle, right, to make some NADPH. That's the whole purpose of everything. We want to go out there, make some NADPH, and when we're done with that, we can come back to glycolysis, but the purpose of NADPH is going to be for certain reductive reactions that we're going to talk about. That is what your pentose phosphate pathway is all about, right? Let's put into perspective with the big picture once again. If you look at the big picture, guess what? This is glycolysis, going all the way from glucose to glucose 6-phosphate to fructose 6-phosphate, going all the way down to pyruvate. That's my glycolysis. But in the very beginning, after I made glucose 6-phosphate, before we continued, it took a detour around, right? Glucose 6-phosphate took a detour around through to make 6-phosphogluconolactone and your ribulose 5-phosphates before coming back to fructose. Now, it can still go forward directly, but it can make this loop if we need NADPH. The end result of this is we make NADPH. That was the only reason why we made that loop out there. That is your HMP shunt. That's why it's called a shunt, because we just went out a little bit, but we came back to where we started from, right? Or came back to the next step. Okay. So that's a summary, but if you wanted to, let's look at the details of what's really going on in your HMP shunt. Okay. So there are two phases of it, right? Two phases, your oxidative phase and your non-oxidative phase of your HMP shunt. Okay. But flow with me right here. This is glucose 6-phosphate. Obviously, that came from glucose. And glucose 6-phosphate goes to fructose 6-phosphate, right? And fructose 6-phosphate goes to fructose 1,6-biphosphate, okay? Excuse me. And then that's going to split into your DHAP and glyceraldehyde phosphate and all that. Excuse me. So this looks very familiar, I hope by now, because you can see that what we have going on here on this side of things is what? Glycolysis. Okay, coming down from glucose all the way through this, that's glycolysis, because at the end of the day, the end result of all of this is going to be what? Pyruvate. So that's glycolysis. But we said that somewhere in there, we made a loop around, right? We made a loop around. And the most important thing that came out of that loop was that we made NADPH. Okay. But now we just need to know the enzymes involved in that loop. Okay. The very first one is going to be your glucose 6-phosphate dehydrogenase, aka your G6PD enzyme. Very important. Your G6PD. Okay, so that's the enzyme that's going to allow you change glucose 6-phosphates to 6-phosphogluconolactone, right? And this is one of the first steps when we make NADPH. Okay, and then from there, your 6-PG can go to ribulose 5-phosphates. We make NADPH there again. Okay, and then the ribulose 5-phosphate, with the help of an isomerase, just rearranges the structure, gives you a ribose 5-phosphate. Okay. And then your ribose 5-phosphate is what can now return to glycolysis back to your fructose 6-phosphate. And the enzyme there is going to be your trans-catalase. Okay. So what are the secondary effects we get out of this? Someone had a question? Okay.
Yeah, I have one question very quick.
Yeah.
Yeah, before we did pentose pathway, we talked about the glucose 6-phosphatase. Main purpose of that is doing gluconeogenesis to get the glucose, correct?
Right, right.
Okay, thank you.
Okay, no problem. So once we make ribose 5-phosphate, then we can come back to fructose 6-phosphate, right? But one thing to remember, right, is that your ribose 5-phosphate, okay, your ribose 5-phosphate actually helps you with nucleotide synthesis, right? We're talking about our purines and pyrimidines. All right, so those are the advantages of making that loop out. Okay, those are some of the advantages of coming out there. All right, but the bottom line is we still return to glycolysis, right? We left as glucose 6-phosphate, right? We came back to fructose 6-phosphate, but along the way, while we were out, we've made ribose that could help with other things, and we've made NADPH that you're going to see is very important in some reductive reactions, okay? So that's the key thing here. One other important thing to remember about this step is that unlike your glycolysis and everything else down the road, there is no ATP used or produced here, right? No ATP usage, no ATP production. It is not part of glycolysis. It is not to make ATP. It does not need an ATP investment. We just took a detour to make some things by the way, like NADPH. That's pretty much what it is. Okay, so where are the areas where we can find these kind of things taking place, right? Your mammary glands, right? The liver, right? The adrenal cortex, right? And also, so your red blood cells. These are the places where you can have this reaction taking place. So let's talk about G6PD, right? And its deficiency in detail, right? We've seen that G6PD is helpful, right? In making your 6-PG, but along the way, right, we made what? NADPH. So what's the importance of NADPH, right? We said it's important for reduction. The exact substrate that NADPH needs to keep reduced is glutathione, right? So I'll illustrate it with this picture. I'll use this picture to illustrate it, okay? So walk with me here. Let's start on the left-hand side. On this left-hand side, I see glucose 6-phosphates, and I see my 6-phosphogluconolactone. Okay, what is this? That's my HMP shunt. Do you agree with me? That's HMP shunt. Because we saw that the very first step of my HMP shunt is to go from glucose 6-phosphate to 6-phosphogluconolactone, right? And the enzyme that did that is my G6PD. And we saw that along the way of doing that, what did we make? We made NADPH. And that's what you're seeing right here, is in the process of using G6PD to go from G6P to 6PG, what have we made? We've made NADPH, period. Okay. Now we get some question. Okay, we have NADPH, that's a start. But what's the essence of having NADPH? Now we move to the right. On the right side, we're going to see why we need NADH. Not an NADPH. Okay. So let's talk about glutathione. There are two types of glutathione. Glutathione can be oxidized or reduced. The oxidized form of glutathione is called your GSSG, right? So GSSG is oxidized glutathione. Whereas GSH, that's your reduced glutathione. Okay, that's your reduced glutathione. So the deal is the enzyme that can take an oxidized glutathione to reduce. And another way to remember this helps me, right? If you get confused between GSSG and GSH, what I always tell myself is that the reduced one is a smaller one because it's been reduced. It's 3 letters, GSH. GSSG is 4 letters, right? So if you're going from 4 to 3, it's been reduced. That's, to come up with whatever works for you, but you have to remember this sense. I always tell myself GSH is a small one, so it's reduced glutathione. Okay, and GSSG is the bigger one, so that's oxidized, right? So obviously the enzyme that's going to help you reduce your glutathione is the enzyme glutathione reductase. And guess what that enzyme needs? It needs NADPH. So in a nutshell, we can say, in summary, that NADPH helps reduce your glutathione. Okay, so we can say that if I have NADPH, the end result of that is going to be an increase in GSH. More NADPH means more GSH, because look at the direction of the arrow. When I have NADPH, which way am I going? I am going towards GSH, which is my reduced glutathione. Okay. So what's the fuss about reduced glutathione? Okay. Reduced glutathione is good because reduced glutathione helps you detoxify free radicals and peroxides, right? It is very functional. So classic example, if you keep going on the right side, what is this? That's hydrogen peroxide. It is toxic. Now, sometimes you're going to need it, especially when it comes to killing bacteria, but we're going to get there. But generally speaking, hydrogen peroxide is a peroxide. It is toxic. It can generate free radicals. But what does reduced glutathione do? Look at the direction of the arrow. It can change that to the most neutral substance on earth, water. So you can see that's the importance of having reduced glutathione, is it can neutralize toxic things to something as simple as water. But now you must remember, as important as reduced glutathione is, without NADPH, you don't get reduced glutathione. So if for any reason someone has maybe G6PD deficiency, now we'll see this in hematology again. When you have G6PD deficiency, it means that you cannot make NADPH. Okay, so that's the first thing that shuts down. And if you cannot make NADPH, guess what you cannot do? You cannot reduce glutathione. Okay, and if you cannot reduce glutathione, guess what you cannot do? You cannot neutralize anything. So what's going to accumulate? All right, peroxides. All right, peroxides like hydrogen peroxide would accumulate, and other oxides. So the bottom line is your organs, right, where we have your HMP shunts taking place, become prone to oxidation. In the absence of G6PD, they become prone to oxidation from oxidizing agents, right? And what are the places? Remember we said your HMP shunt doesn't quite happen everywhere. There are specific places where it happens. And one of those places you must remember is what? The red blood cells. Now it happens at adrenal cortex, liver, your lactate mammary glands, but the most important one where your HMP shunt happens is your red blood cells. So if I have a G6PD deficiency, my red blood cells can be affected. That's the reason why G6PD deficiency that you see here in biochem becomes a hematology topic as well, right? Because my HMP shunt happens in red blood cells, okay? So what that means is now I'm gonna have red blood cells in G6PD deficiency. I have red blood cells that are prone to oxidation, right? So if I get exposed to oxidizing agents, you must remember the kinds of oxidizing agents you have. For example, your fava beans, oxidizing agents, your sulfonamides, nitrofurantoin, right? Your malaria medications, primaquine, chloroquine, antituberculosis drugs. These are all oxidizing agents, okay? And when you get exposed to them, what happens? You get oxidation of your hemoglobin, okay? And then oxidative damage sets in. But what specific oxidative damage do we get, right? So now I have a red blood cell. Let's make a sketch real quick. This is my normal red blood cell with hemoglobin and everything in there, right? But now if I have G6PD deficiency, this red blood cell is now prone to oxidation. And because it's now prone to oxidation, what's going to happen is oxidation takes place and I develop what's called Heinz bodies on the inside of my red blood cells. All right. And what are Heinz bodies? These are just denatured hemoglobin from what? From oxidation. This is the reason why you cannot have oxidation, because you don't need Heinz bodies. But it doesn't end there. The problem with Heinz bodies is your splenic macrophages don't like them. Okay. So, or you can say they like them, right? You can look at it like Heinz ketchup, all right? And your splenic macrophages likes them. So what do the splenic macrophages do? They bite them off and you end up with a cell that's been fragmented, all right? So now your red blood cell looks like that. And that's what you call your bite cell. Why? Because your splenic macrophages have taken a bite, all right? What they're going to do is they're going to try to take a bite to bite off the Heinz bodies. Okay, so we'll talk about this again in hematology, but now we're just trying to link it to the biochemical part of it. And it all came down to NADPH, right? Because without G6PD, there is no NADPH. Without NADPH, we do not reduce glutathione. If glutathione is not reduced, then we are prone and exposed to free radical damage and oxidative damage. That's the reason why you need your G6PD, okay? All right. So moving on, right? The next two topics there is your disorders of fructose metabolism and galactose, right? And they're very similar, you're going to see. Fructose and galactose, they kind of like do the same thing, okay? So let's start off with the fructose side of things. The fructose side of things, you have two, all right? Just like galactose. You can have essential fructosuria, right? And you can also have your hereditary fructose intolerance. Two different spectrums. All right. But actually, before we even do all of that, let's take a look at the table. Let's take a look at this. I have fructose going to fructose 1-phosphates. Okay. And fructose 1-phosphate can split into my DHAP and glyceraldehyde, giving my glycerol, all right, and all that. But I want to connect the dots here. Let's go back to the beginning. All right. So this is page 80. Just remember. I want to connect the dots for you here. All right, let's take a look at this. We've seen, and like I said, always come back to this page and it brings the whole picture together. This is glycolysis, right? Glucose, G6P, F6P, F16BP, blah, 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 end up in pyruvate, that's glycolysis. But take a look at the side. Fructose changing to F1P, to glyceraldehyde, and they're coming in here. So you can see the moral of the story here is fructose has the ability to enter into glycolysis as well. Glycolysis does not have to start with glucose. It can also start with fructose. And here's what's unique. Remember, my rate limiting step of glycolysis is number 7. That's my rate limiting step. Okay, number 7, my phosphofructokinase 1 is my rate limiting step of glycolysis. And don't forget that your rate limiting step means it's your slowest step. Okay, so when I start here, even if I'm high speed, once I come to this point, I slow down. I slow down, right? And then I keep coming down. But what's unique about fructose that you must remember is that fructose enters glycolysis below the rate limiting step. It comes in after the rate limiting step. So fructose breakdown can actually provide you with quicker energy than glucose. Because glucose will have to go through that slow stage. Fructose does not. Fructose comes in lower here. So remember that. You can see it in the question. Which one is going to give you ATP faster? The answer is going to be fructose, because fructose enters after my rate limiting step. So why am I bringing this up now? When we talk about the disorders of fructose metabolism, like essential fructosuria and all that, this is the area we're playing with right here. Okay, so when you're reviewing and you're looking at that, come back and make the connection that that's also another way to get into glycolysis. Okay, so let's go back to where we were. Nope, nope, no, went too far. Okay, all right, so here we are. So when you look at it, fructose, fructose 1-phosphate, and all that, once you get to DHAP and glyceraldehyde, what is this? This is glycolysis, all right? So this means we're entering into glycolysis after the rate limiting step, okay? That's one. But that aside, let's look at some key things on this side of things. The very first enzyme to start the fructose action is fructokinase, because fructokinase will actually change us from fructose to fructose 1-phosphate, okay? ATP requiring process. Then there's another enzyme called the aldolase B that will actually changes, to your DAP and glyceraldehyde. And your aldolase B is the one that would actually enable us to get into glycolysis, okay? So with your fructose disorders, we tend to focus on just, now the other enzymes, but we tend to focus on these two, is what happens if I'm deficient in fructokinase, and what happens if I'm deficient in aldolase B? But here is the deal. Your fructokinase, if you use fructose as the benchmark for starting this whole thing, okay? Fructose, I always think that's how I like to study biochem. I like to think of options. Fructose has options as well. With fructokinase, it can change to fructose 1-phosphate, right? And keep going that way and enter glycolysis one way. But it doesn't have to all the time. There is another form, which is your fructose 6-phosphate, that a hexokinase can do for you. Fructose can also, now doesn't always happen, but fructose can change to fructose 6-phosphate with hexokinase. So it has options, and I'll tell you why that option is important. Let's start off with a scenario where I'm deficient in fructokinase. Immediately, right, what's going to start accumulating is what? Fructose, because I can't go forward. I have blocked this step right here. So fructose immediately begins to accumulate. Okay. However, this disorder is not so bad because key points, right? And it says it right here. It's not so bad. It is considered to be kinder because fructose is not trapped in cells. Why is fructose not trapped? There's a way out with hexokinase. So the body says, hey, if we cannot make F1P, we can make F6P and it's going to be all right. That is what makes this disorder mild. Now, initially, yes, we're going to get a lot of fructose floating around, and some of that fructose is going to show up in your urine which is why it's called a fructosuria. Okay, but ultimately it's not that bad because guess what? We have a way out, right? We have a way out, and the way out is we can go to fructose 6-phosphate with hexokinase. Okay. Now, what about the one called your hereditary fructose intolerance? That is a more serious scenario. Okay, because this is a deficiency of your aldolase B. Both of them are autosomal recessive. Okay, aldolase B. Now, let me tell you what makes this one a problem. Okay, what makes this a problem is that when aldolase B is blocked, guess who's the first thing to accumulate? Fructose 1-phosphate. The message here is there's a difference between wasting just fructose versus wasting fructose and phosphates. The difference between fructose and fructose 1-phosphate is there is a phosphate here. Okay, so with this scenario, when F1P accumulates, the problem is that we're not just throwing away fructose, we are throwing away phosphate that we need for other things, right? So you have a decrease in available phosphate, and I need phosphate for what? I need it, right, for glycogenolysis, right? I need it for gluconeogenesis. I need it for so many different things, okay? And if I don't have phosphate, these things will start going down, okay? So what are the symptoms, right? This, let me correct this. This is not glycolysis, right? This is gluconeogenesis as well. So when these things start going down, ultimately, what's going to happen is that, good, is that we don't make glucose. Because watch this. Remember I said the two ways you can make glucose, literally like old money and new money, is glycogenolysis or gluconeogenesis. It's either you go to work and make some new money, or you go to the bank and withdraw your money, right? Both of these processes require what? Phosphates. So if I have F1P accumulating and I'm wasting phosphates, I cannot make money. I cannot make glucose, right? So these get affected, all right? And one of the symptoms you're going to see early on is going to be what? Hypoglycemia. That is how you know it's hereditary fructose intolerance. Hypoglycemia is going to set in. And the presentation as well. Look out for the baby or something, a kid, right? That every time they consume fruit juice or honey or something, something with a lot of sugar, then they start reacting. So it's almost like you can't take sweet stuff. You have an allergy. It's almost like you have an allergy to the sweets, right? That tells you there's a fructose intolerance. Okay. So look out for that. So if someone is hypoglycemic, but you can't even give them a sugar drink because then they will get even more hypoglycemic, right? And then you get more systemic symptoms like jaundice, cirrhosis, vomiting. That is how you know that it is your hereditary fructose intolerance. You won't see this level of symptoms in fructosuria. Fructosuria is so mild because we have an escape, okay? So how do we treat this? Is number one, avoid fructose, because that's the problem, right? Avoid fructose because you don't have a way of breaking down fructose and you're going to just accumulate F1P and now you get into trouble. So avoid fructose completely, all right? Avoid sucrose because sucrose has fructose and a lot of table sugars we use have fructose in them. So sucrose, avoid that, okay? And also avoid sorbitol. We'll come to sorbitol shortly because sorbitol can be changed to fructose. So avoid fructose or anything that can change to fructose. Sorbitol is one of them. That's how you can manage this scenario, okay? So that's from the fructose side of things. Now you can also have galactose problems. Very similar to the fructose side, very similar, right? So the way I like to think about it, your galactokinase deficiency is similar to your fructokinase deficiency, right? The only thing is, yeah, this is called essential fructosuria, but if you want it to be nice, this is almost like a galactosuria you're going to see, okay? But you also have classic galactosemia, which is the more severe one, right? That is kind of equivalent to your hereditary fructose intolerance, okay? But at the end of the day, your galactose problems are always worse than fructose problems. So even your more serious fructose problem is not as bad as a serious galactose problem. Okay, galactose is the worst one. So what's the pathway? Let's talk about the pathway before we talk about the two scenarios. It starts off with galactose. That's the benchmark. That's what we're talking about, right? And once again, galactose has options. Always think about your options. What are the options galactose has? One, it can change to galactitol, okay, with the help of the enzyme aldose reductase. But we always don't want that, okay? Not quite, because galactitol is not good for it to accumulate, okay, because it's a poor osmotic substance, just like sorbitol. But at least sorbitol had an escape. Sorbitol could change to fructose, okay, in some tissues, specific tissues. So yes, it's an option, but yeah, this is not an option we want to exercise all the time, okay? But other than that, galactose, the other option is with the help of galactokinase, which is like a fructokinase, galactose can change to galactose 1-phosphate, okay? And galactose 1-phosphate can ultimately change to glucose 1-phosphate that can generate glucose and put me in the pathway of glycolysis. Okay, so let's look at, okay, what happens when I start losing enzymes? Let's start with galactokinase. If I lose galactokinase, then it means that I cannot make galactose 1-phosphate. I'm unable to go this way, right? I can only go this way. Okay. So galactitol can accumulate. However, that's only if galactose is present in your diet. So relatively mild, okay? But what's the symptoms you're gonna have? When you block this, galactose accumulates in the blood, galactosemia, some of it shows up in the urine, galactosuria, like I said, right? But also the galactitol that accumulates can give you infantile cataracts, okay? But generally, it's a mild condition, just like your fructosuria, okay? But let's talk about the big one. It's a classic galactosemia. The classic galactosemia is almost like your fructose intolerance. This is like, the other, if you wanted to give this another name, even though that's not the name, you can almost call this like a galactose intolerance, right? So it's like you have fructose intolerance, galactose intolerance, right? That's your classic galactosemia. Okay, so the enzyme that's deficient, right, is a uridyl transferase, right? This one, right? The uridyl transferase is deficient. So in this scenario, what happens is you block this one, you block that one. Okay, so what accumulates? Everything, right? Galactose will accumulate, all right? Galactose 1-phosphate will accumulate, galactitol will accumulate as well. Everything downstream this way will begin to accumulate. Okay, so galactitol, for example, can accumulate in the eyes, right? And that's why you can have eye symptoms, right? And cataracts, just like your galactosuria, but or like your galactokinase deficiency. But just like your fructose, we're also accumulating phosphates as well. We're wasting phosphates, okay? So we have more serious symptoms going on, okay? Like just like we saw in the other one, like jaundice, and failure to thrive and all that, okay? How is this question going to present? Look out for a baby that it's almost like the baby's allergic to breast milk, okay? So it means the baby is fussy, but when the mother tries to breastfeed and give the baby some breast milk, right? Then the baby, starts developing jaundice, and all that kind of stuff. And the baby just gets worse every time you try to feed the baby with breast milk or formula, right? Then that's how you know that this baby is kind of like intolerant of galactose. So they're very similar. In this other one, it's like you can't tolerate fruit juice. In this one, you cannot tolerate breast milk or anything like that. That's your classic galactosemia. Okay. So obviously the treatment is remove galactose and lactose from the diet. All right. Remove galactose and lactose from the diet. All right. And then sorbitol, let's talk about sorbitol. Remember we said sorbitol had a way out. It's like galactitol, but it had a way out. You could change your fructose. Galactitol cannot. Galactitol is stuck as galactitol. Okay. So just like galactitol, right? Your sorbitol is an osmotic substance. Okay. It's an osmotic substance that can actually draw water towards itself, right? So overall, sorbitol is a way of trapping glucose, right? Yeah, so sorbitol, it ends in ol, just like galactitol, ols, right? Take it back to organic chemistry, ols are alcohols, okay? So what's the mechanism here? Glucose, with the help of the enzyme aldose reductase and NADPH, can change to sorbitol, right? And some tissues have this, okay? And then sorbitol can change to fructose with the help of the enzyme sorbitol dehydrogenase in specific places, right? It is not an all for none. So there are some places, right, as you're going to see very shortly, that can only do the first step and you stop there. Others have the ability to go all the way, okay? So the problem is if you don't have the ability to go all the way, you're in trouble if you get stuck here. Because now you're just like galactitol, right? We know that the option of going to fructose is there, but now you're in a part of the body where that option is really not there, okay? So for example, something like your lens, like it says right here, your lens primarily has aldose reductase, okay? So that means that it can change glucose, right, to sorbitol, right? And also it says like your retina, kidneys, and Schwann cells have only aldose reductase. So it means that they'll only go here, right? The lens can go all the way, depends on accumulation. But the moral of the story is that for all of this, right, your lens, right, your retina, your kidneys, right, your Schwann cells, the buck stops here with them, period. That's the moral of the story. All of these listed here, this is where it ends for them. It ends in sorbitol. So, which means that in these people, if they develop hyperglycemia, diabetes, right, then all that excess glucose can get changed to sorbitol and you're stuck there. And now sorbitol can exert damage on distance, right? When the sorbitol starts damaging, how is it going to cause the damage? Right? We're going to do this in endo, but diabetes has two forms of damages that it causes, right? Diabetes damage is either typically through osmotic damage or what's called your non-enzymatic glycosylation. So the osmotic damage is when glucose can change to substances like sorbitol, right, that can draw water in, right? These are considered osmotic substances. They can draw water in, and that water accumulation can destroy the tissue. That's what's happening right here, right? So that's how you get kidney damage from diabetes, right? Your retina, your lens, that's how you get eye damage and cataracts and all that stuff from diabetes. Your Schwann cells get destroyed, your peripheral nerves, you get diabetic neuropathy. This is the mechanism from a biochemistry standpoint, is the glucose, excess glucose gets stuck, right? As sorbitol, okay? All right. So the thing about it is, so that's one, but also don't forget the galactose, right, can also get stuck with galactitol using the same enzyme, make the connection, right? Galactose changing to galactitol, what enzyme is doing that? Aldose reductase, right? And obviously, excess glucose can bring you there. It's the exact same thing here, same enzyme, aldose reductase, giving you sorbitol, okay? Now, in certain other organs, right, like your livers, your liver, your ovaries, your seminal vesicles, they have both. So it doesn't end here for them. All right. So in your liver, all right, your seminal vesicles, your ovaries, if you have excess glucose and excess glucose is changed to sorbitol, no problem. We're just going to get back to fructose. Okay. So that is why you must remember the areas where we get stuck. which is your lens, your retina, your kidneys, and your Schwann cells. Just think of the places that diabetes damages. Those are the areas where you get stuck, okay? So that's it all. And moving on to your lactase deficiency, you won't spend too much time on this, right? I mean, this is straightforward, like the lactose intolerance. I think everyone kind of knows the symptoms, right? The bloating, cramps, flatulence and all that. And typically, it's because of the deficiency of the lactase enzyme, okay? So you develop a lactose intolerance pretty much, okay? And kidney, you need to know is, all right, there's an enzyme, but where does that enzyme work? Okay, where is the site of action? Where does it get its job done? It gets its job done at your brush body. Okay, and that brush body helps you digest your lactose that you have in your milk and milk products, and it breaks down that lactose into glucose and galactose. That's why we're talking about it right here. Okay, so different types of lactose intolerance can occur. You have the primary one, which happens with most people, right? This is a more common one. It's age dependent, because a lot of times if you're lactose intolerant, most likely you remember that when you were younger, you were fine. But as you got older, you start losing. Same thing happened with me. When I was younger, I was fine, but now I'm lactose intolerant, okay? I mean, it's multifactorial, but this is your age dependent decline, right? In your ability to process your lactose, okay? And then you can have secondary, right? Secondary is not an age-dependent decline. Secondary is typically secondary to something, an infection, right? Secondary to an infection, right? Especially a viral gastroenteritis, right? Or an autoimmune disease, okay? That could be secondary as well. So especially someone that's had a rotavirus episode, you lose your brush butter enzyme, you get the flattening of those villi tips, and in the process, you become lactose intolerant, okay? And then you can also have your congenital lactase deficiency, right? Due to defective gene, right? And that can be rare as well. So from a physiologic standpoint, right, what are you going to see in the stool? Decreased pH, right? These are the markers you have to remember. Just memorize these ones. Very important. Decreased pH, okay? And also you can have increased hydrogen contents, right? With your lactose hydrogen breath, right? Because remember, decreased pH goes together with more hydrogen. It's almost like creating an acidic environment, okay? So remember that. And also, if you were to do a biopsy in those that have, especially your primary lactase deficiency, you're going to see that the biopsy is going to show you a normal mucosa, right? Because it is not a structural problem, okay? And the management here obviously is avoid dairy products or, add lactase pills to your diet, okay? So that's that. And over here we have amino acids, the different types of amino acids, the acidic and basic, right? So that's straightforward. The last thing here is your urea cycle. Let me see if I can touch on this real quick before we stop for today. I'm trying to cram in as much as we can today. Your urea cycle has one job, okay? And that job is to get rid of excess urea from the body, right? And where's your urea? Your urea is your breakdown product of your protein. If your protein breakdown, it's the end result of your amino acid catabolism, okay? So the end result is when you look at an amino acid, the name amino acid means it has an amino group and a carboxylic acid group. The amino group is your NH2, the carboxylic acid group is your COOH. Okay, so every amino acid must have these two. So guess what's unique in there? Nitrogen. So when you break down amino acid, when you break down protein, you release a lot of nitrogen, right? And nitrogen, excessive amounts of nitrogen in your body is not good. So we need to get a way to get rid of this excess nitrogen, okay? That is where urea comes in. Urea is just a way of taking all the nitrogen we're getting from protein waste and removing it from the body, okay? And that's why if you actually look at the structure of urea, what you keep seeing in urea is nitrogen. Nitrogen is what you see in urea, okay? But really and truly, how is this nitrogen coming together, right? this nitrogen is coming together as ammonia, right? Which is your NH3. So that's how it gets into your urea cycle, right? You have ammonia, which is NH3, and this could be in the form of glutamate that comes in, right, with the help of the enzyme CPS1. You generate carbamol phosphate, and then you go through the urea cycle, and the end result is you get urea that goes to the kidneys. Okay. Time won't permit, but one thing to remember about this is just like we did your citric acid cycle, try to remember this, but even if you don't, remember the step where the urea was actually made and the enzyme that actually made urea. If you don't remember anything else from this cycle, remember that, and that's your arginase. Arginase is a step where arginine changed to ornithine, and in the process, we release urea that can go to the kidneys and get excreted. Okay. The other thing that's important to remember about this is your OTC enzyme, which is your ornithine transcarbamylase, right? So for short, it's called the OTC, right? I talk about this one because the biggest deficiency that you can get in the question that comes out of this is your OTC deficiency. So, I've run out of time, but look it up. Your OTC deficiency, the problem with it is obviously your urea cycle is going to shut down. So you're not getting rid of ammonia, right? So okay, yeah, it's right here. With your OTC deficiency, one of the key things that comes out is excess ammonia, because the urea cycle has shut down. So you get a hyperammonemia. But also, very importantly, remember that in OTC deficiency, orotic acid is going to increase, okay? And the reason why orotic acid is going to increase is because the carbamol phosphate is actually part of your pyrimidine synthesis, right? And in your pyrimidine synthesis pathway, there is orotic acid in there. So when you have an OTC deficiency, the excess carbamol phosphate gets shunted to your pyrimidine synthesis pathway, and you get an increase in orotic acid. Very important, okay? So that is why when you come here, one of the findings is orotic acid. However, I'll end with this. An increase in orotic acid does not always mean OTC deficiency, right? Because there is another diagnosis called your orotic aciduria, where you actually also have increase in orotic acid, right? But orotic aciduria, remember this, it is a pyrimidine synthesis defect. Okay, it's a pyrimidine synthesis defect. So because of that, ammonia is going to be normal, all right? That's the difference. Normal ammonia there in pyrimidine synthesis defect, but normal ammonia increased orotic acid, whereas in OTC deficiency is increased orotic acid and increase in ammonia at the same time, okay? So remember that. All right, so that's where we'll stop for today. So on Monday we will resume and pick it up with something else. Okay, so just take some time and review everything we've done today, and also try to read ahead. And like I said, if I can squeeze in some extra sessions somewhere to cover some more biochem, I'll try my best to do that. All right.
Doctor?
Yeah.
On Monday, you're going to have a lecture from 6 to 8.
Yeah.
What will you be focusing on? Since next week we're starting immuno and micro, will you start off with immunology mostly?
Yes.
Or,
yes.
Okay.
Yes.
Okay, thank you.
No problem. No problem. All right. Thank you, folks. I hope this is helpful for you. And this is how we're going to do it. And we'll run through as much as we can.
Just one question.
Yeah.
With regards to this recording, where would we be able to access it?
I believe, it'll probably be in Canvas. Dr. Oleski will find a way to put it up there. So, yeah, just follow up with Dr. Oleski for the recording.
Okay.
Dr. Kiki, I have one quick question. So anti-malaria medicine like chloroquine, hydroxychloroquine and all this. Okay, so that is breaking our red blood cell membrane. So that's not good to take, obviously, if we don't have to. Now, when people take that, obviously does the job of oxidizing RBC membrane.
Yeah, I mean, its job is not to oxidize red blood cell membrane. I mean, that's one of the effects that you experience with it. So obviously they have their good effects, but you know, the other side of it is these could be oxidizing agents. And if you have a G6PD deficiency, then you're prone. Now, if you don't have G6PD deficiency, then no problem. Okay, but
You mean even take hydrochloroquine, that's okay? Hydroxychloroquine?
yeah, in this regards. Now, there are other side effects you can get with things like that. But in regards to G6PD stuff, which is what we talked about today, if you don't have G6PD deficiency, then you don't have any problem with oxidation. Okay. It's only when you have G6PD deficiency, you're prone to oxidation, and any oxidizing agents could affect your red blood cells.
Okay, so it gonna give it to side effect to everybody, but G6PD deficiency people gonna have more prone to with this medicine. That's what you're saying.
Right, right.
Okay, so now this oxidizing thing process is that because GSH is a good one, reduce the glutathione. And this one is that neutralizing the toxin, which is high peroxide,
Right.
hydrogen peroxide. So it's kind of like a neutralizing the toxin, right?
Pretty much. That's the message there, is reduced glutathione helps you neutralize things. Okay, so you always want to keep your glutathione reduced.